Okay. Well, thank you everyone for joining us, and thank you to our speaker, Moncef Soussi. I hopefully pronounced that close.
You did.
Thank you. There was a question, is this webinar all online or also in person too? It is online only. We had planned on doing a in-person aspect to it. And for those few people who did sign up for the in-person, I apologize. We did issue refunds to those of you who did that. But unfortunately, I was going to host it at my office, but I have come down with COVID and there's been a few other cases at our office. So we decided it was best if we just held it online only. So I will go ahead and introduce our speaker. Let's see. Dr. Soussi joined Cantsink in March 2019 after completing his Ph.D. at Colorado State University. His thesis was titled The Helical Pile Capacity to Torque Ratio, a Functional Perspective. And his paper was about torque correlation factor, also the KT, and was published in the DFI Journal in 2020. Before joining Cantsink, Dr. Soussi was working as a project engineer at CTL Thompson from 2003 to 2018, and during that time, he was one of the key architects in expanding CTL Thompson's testing capabilities on all things helical piles. So with that, I would like to invite Dr. Soussi to give his presentation. Thank you.
Thanks, Peter. Thanks, everyone, for attending this, I call it guest lecture about Introduction to Helical Piles. My name is Moncef Soussi, and I come to you from Cantsink. As you see, today I'm going to be introduce you to helical piles. Usually, Cantsink will provide like 3 different lectures. The first one is about Introduction to Helical Pile. The second one is about designing helical pile. And the third one is about special topics, such as buckling, corrosion, expensive soil, lateral loading of helical piles. So I hope after this 1 hour and 15 minutes of speaking, I will hope that you will have a pretty good idea about what helical piles are, how to determine the pile capacity, because you need that to be able to design helical piles. So let me introduce myself. This is my background. Like Peter said, I've been working with helical piles for the last 20 years and mostly with CTL Thompson. CTL Thompson is a company there in northern Colorado. Fort Collins is part of is the branch of CTL Thompson in northern Colorado. CTL Thompson is a geotech firm in Denver, and it has like about 6 or 7 branches in Colorado and Wyoming. And when I joined CTL Thompson in 2003, at that time, I didn't work that much with helical piles. I know about them, but I didn't work that much with them. So my boss came to me and he asked me to do some, L-pile analysis for helical piles. And I said, what helical piles? What is it? And since then, he introduced me to helical pile, and since then, I've been working with helical piles. So in 2003, we don't have testing capability for helical piles. Now, let me give you a brief history. Helical piles has been around for 100 years, you will see later on, but they became so popular in the last 30 years or so. That's because of the advancement in installation machines. Okay, so in the last 30 years, they became so popular. And yet, when you go to the IBC code, you don't find helical piles there. So in 2005, there were about 9 or 10 helical pile manufacturers, among which Cantsink. They get together and they form an ad hoc committee, and they talked to ICCES. ICCES is a subsidiary of ICC. ICC is the International Code Council that issues all these building codes, such as IBC and IRC. And ICC didn't exist before 2000. Before that, there were like so many different codes, like 4 or more codes in the United States. So these companies, they get together and they wanted to unify the whole thing and the one single code. So they formed ICC. And the first IBC, which is issued by ICC, was issued in 2003. And usually this IBC code, it issues every 3 years. So in 2003 and 2006, helical pile, they are not in the IBC code because it's like they're new, okay, and they're not in the IBC code. These helical pile manufacturer, they decide to talk to ICC-ES, which is a subsidiary of ICC. ICC-ES evaluates product such as helical pile when they are manufactured in the plant. They are not like when you install them, they just manufacture in the plant and they take them to the site and they screw them in, okay? So they decide to talk to ICC-ES to obtain an ICS report. And since there is no accepting criteria at that time, so CTL Thompson is independent. We're not manufacturer of helical piles. So this ad hoc committee, they decide to choose us to write these accepting criteria AC58 with ICC-ES. So we started in 2005 and we finished this accepting criteria in 2007, and it was issued in 2007 by ICC-ES. And this criteria basically gives the requirement for the manufacturers, okay? This manufacturer has to meet these requirements to obtain an ICCS report. And the purpose of that ICS report is an evidence that your product is code compliant. And it helps you a lot with the building official, building department, design engineers, architects. It helps you a lot, especially for this product, like I say, is new, because we know traditional deep foundation, drilled piers, driven pile, all this, they are there. But these are new. And therefore, when you have this ICS report, it helps you a lot, like I said, with these building officials and building department. AC58, AC stands for accepting criteria. So whenever you have a new product and you want to have an ICS report, if there is not criteria about that product, you have to work with ICC-ES to create an accepting criteria. Okay, so that's what happened with the helical pile manufacturers. AC stands for accepting criteria. So what happened with these helical pile manufacturers, they went to ICC-ES, they want to have an ICS report, but there is no criteria at that time. That's why CTL Thompson and ICC-ES, they work together with this manufacturer to produce these accepting criteria 358, and that's only for helical piles. There are so many accepting criteria. If you go to the website of ICC-ES, you will find probably hundreds of them for each product. For helical pile, it's AC 358, and it used to be 3 until like about 5 years ago. If you go to ICC-ES website, you can get AC 358 for free. But for some reason, there is another evaluation agency in the United States, and it's called IAPMO. Okay, so the big two is, or ICC-ES and IAPMO. IAPMO, I believe, like about 5 years ago, before that, they didn't really evaluate structural product. But 5 years ago, they started doing that. And it seems to me there was a conflict between both of them. And ICC-ES started charging $300 for these accepting criteria 358. And for educational purposes, it's for educational purpose only. If anybody needs it for educational purpose, I'll be happy to send him AC 358, okay, because it's copyrighted. I get this accepting criteria from them because I work with them most of the time with helical pile. So in 2007, I worked in CTL Thompson and we established an accredited testing lab, because AC58 requires that the testing of helical pile to be done by an accredited testing lab. Okay, so we decide to have an accredited testing lab, and this accreditation body, there were like about 7 or 8 in the United States at that time, which chose IAS, International Accreditation Service, and it took us like about a year or two to get our accreditation from IAS. And if you go to IAS, that stands for International Accreditation Service. It's also a subsidiary of ICC. If you go to their website and you look for testing lab number 342, you will see CTL Thompson. And the scope of accreditation is testing helical pile per AC58. So when we got our accreditation from IAS, all these manufacturers, they came to us, okay? So almost every helical pile manufacturer in Canada and the United States, I tested their helical piles, because we are the only accredited testing lab. And until now, I don't think there is any other accredited testing lab for helical piles. It's still only CTL Thompson in the United States and Canada. So that's how it started, with these accepting criteria 358. Then people, they start testing their product to obtain an ICCS report. And like I said, the purpose of that ICCS report, it proves, it's an evidence that your product is code compliant, and it helps you a lot with building official, building department, engineers, architects. I've seen one time I was talking to one of these inspectors, and he told me during the 2008 they laid off so many people, and he was sending these people to inspect product, and he was telling him, listen, if it has an ICS report, check. If it doesn't, then we have to ask so many questions. Don't. So you can see that if you have an ICS report for your product, that will help you a lot. I was also the chairman of the ad hoc committee who revised AC 58 in 2013 and 2017 and also 2020. The latest version is August 2020. I'm an active member of the Helical Pile Anti-Back Committee. This committee is within DFI. DFI is the Foundation Institute. We meet like twice a year and we discuss helical piles. And most of the time, whenever there is an annual conference, like annual conference for the Foundation Institute or Super Pile, these are sponsored by DFI. We meet there, and anybody can call in. You can really call in and get into the meeting. I also presented helical piles testing results at DFI conference. Like I said, I test almost all of these helical pile manufacturer product who received an ICS report. And also when I was in Colorado, in 2003, I was doing my PhD, and my thesis was seismic-based isolation of low-rise structure building using geosynthetic. But I have to go home. I have to leave the United States for personal reason for like 3 years. When I came back, somebody did that seismic-based isolation. So basically, I quit. So in 2015, I went to work. My advisor contacted me and said, listen, you have all these test results from helical piles. Why don't you just change your subject and finish your PhD? So I went back in 2015 and I finished my PhD in 2019, and my thesis was about capacitor torque correlation, that torque correlation factor, KT. I'm going to talk a lot about it, and that's what my PhD was about. And I really think that the capacitor correlation is probably the most significant attribute of helical piles. And you will see later on why. Now, today's topic is, like I said, an overview, installation and application, and design theory. I'm going to show you how to determine the pile capacity. It's not really that hard. It's easy, because designing a helical pile for an engineer, when you ask an engineer to say, design a helical pile, basically, designing a helical pile is coming up with the shaft size. What is the shaft size? What is the helix configuration? Is it a single helix, double helix, triple helix? What is it? Then you have to come up with the minimum depth and the minimum required installation torque. Okay, that's what does mean a helical piles design. So here's what the overview is. We're going to define what a helical pile is. I'm going to show you some common helical pile anchor and components. I'm going to show you the benefits of helical piles. And of course, I have to talk about the history of helical pile. Who invented the helical pile? Who is considered the father of helical pile? Like when we say the father of soil mechanics is Carter Zaghi, Alexander Mitchell is basically considered the father of helical piles. So what is a helical pile? A helical pile basically is a steel central shaft that has these helical plates welded to it. It's very simple. It's a steel, it's not concrete. It's steel central shaft that has these helical plates welded to it. We call them helical plates, we call them blades, we call them helices. They're welded to that central shaft. And that central shaft could be a round hollow shaft or a solid square shaft. Now, I've seen there are some hollow square shafts, but the most common square shaft is the 1.5 inch square shaft and the 1 3/4 square shaft, and these are solid, and they are used as helical anchors. They are so strong, okay, and most of the time they are used in tension. That's why we call them a helical anchor. If a helical piles application is in tension, we call them helical anchors. The round shaft, the most common one is the 278-inch outside diameter shaft, the 3.5-inch outside diameter shaft, and the 4.5-inch. These are the most common hollow round shafts out there. And this lecture basically is about small diameter helical piles. Even when you go to the Foundation Institute or some other conferences about helical piles, they're still talking about small diameter helical piles. What does it mean, small diameter helical piles? That means the shaft size has a diameter no more than 4.5 inch. And the reason I choose 4.5 inch because AC58, if you have a shaft that has a diameter higher, larger than 4.5 inch, they will not evaluate it because it's outside of the scope. And the reason why, because most of these data that we've been collecting for the last 30, 40, 50 years, they are based on small diameter shafts. Now, large diameter shaft, they are there and they use them also, but we don't have enough data to really, for instance, say what is the KT value for that shaft size, such as 6.5 or 8.5 inch outside diameter shaft. We don't know. We don't have enough data to say what the KT value for that shaft size. Whereas for these small diameter helical piles, you will see what the capacitor correlation factor KT is. So again, helical pile is just a steel central shaft that has these helical plates welded to it. And the most common type of small diameter shaft is the 278-inch outside diameter shaft, the 3.5 and the 4.5. And for the square shaft, these are solid one, the 1.5 and the 1.75 inch. Okay, these are the most common helical pile anchors out there. Now, the helical pile components, all right, this is what a helical pile. The lead section, we call it the lead section. That's because this is the first section that goes on, that goes into the ground. And you can see, I say section. Helical piles, one of their advantages is that they are installed in segment, okay? We install them segment by segment. So the first section that goes in, we call it lead section. And usually the lead section is the one that have these helical plates welded to it. Helical piles, there is this load, small diameter helical pile, there is this load through these helical plates, okay? And helical pile, they're a type of deep foundation. So we want to make sure that these helical plates, we use deep foundation. Why? Because shallow foundation is probably the least expensive one. But we use deep foundation because it's the soil, the topsoil is not suitable for shallow foundation, or we need larger loads, okay? So we need deep foundation. And since this is deep foundation, the lead section has to be further down so that we can get suitable soil. We have suitable soil there. So the lead section usually is the one that has these helical plates welded to it. Now, if the design engineer needs more helical plates, you can weld helical plates to the extension, okay? So when we install the helical pile, the first one that goes in is the lead section. Then you have this coupling connection, okay? You can add the extension and you keep adding extension until you meet the minimum required torque and the minimum required embedment depth, okay? So you can see a helical pile basically consists of a lead section with these helical plates welded to it. Then you have the coupling connection, then you have extensions. That's what a helical pile component. These are the helical pile components. Now you can see here the pitch. It's 3 inch. The pitch is basically the distance between the leading edge and the trailing edge. And this one is 3 inch. 3 inch for small diameter helical piles. Almost all the helical pile I tested for these helical pile manufacturers, the pitch is 3 inch. So these empirical tests, these empirical equation that we came up from these test results, they are based on a 3 inch pitch. For instance, if you really increase the pitch, the KT value will decrease. So most of these helical pile manufacturers, for the small diameter helical piles, they have a pitch for 3 inches, okay? And then also these helical, segments, the lead section and the extension. The most common length is 5-footer, 7-footer, and 10-footer, specifically the 5-footer and the 7-footer. And also these helical plates, when they are welded to this lead section or the extension, there is a requirement about the spacing between these helical plates. I'm going to talk about later on when we talk about the method to determine the pile capacity, specifically the individual bearing plate method and the cylindrical shear method. There is a requirement between this, about the spacing between these helices. Also, the first helix is always the smallest, okay? And then you can increase, as you go up, you can increase the diameter of the helix. This is to help really install the pile smoothly with minimum disturbance into the soil, So and the most common helical sizes are 8-inch, 10-inch, 12-inch, and 14-inch. These are the most common helical sizes for small diameter helical piles. Okay, when you get to large diameter helical piles, helical shafts, yeah, you can see 24, 48 inches helix sizes. But for small diameter helical pile, the most common helical size are 8-inch, 10-inch, 12-inch, and 14-inch. Here at Cantsink, we have also 16-inch and 19-inch helices approved by ICCS, and our ICCS report is number 1559 because our product is approved by ICCS. And the reason why, because we have sometimes we need more area, and that's why we decide to have the 16 and 19-inch in our ICS report. So these are basically the component of a helical pile. Now, these are common connector, coupler. The most common coupler in helical pile is the bolted one. Now, I've been in this business for like 20 years. There is only one manufacturer that have a threaded coupler, and there is another one in Canada that have a welded coupler. Okay, I've seen them. They go to the field, they install the lead section, they put the extension, they weld it, and they keep welding the other extensions. And the welder takes about maybe 10 minutes to weld the extension to the lead section or the extension to the extension. I've seen only one that have welded coupler, and I've seen one that has threaded coupler. But the most common type of coupler is bolted coupler. This is a square, solid square shaft, and this is a 1.5 inch, and it has one bolt. Of course, when we design helical piles, make sure we design for the mechanical capacity. We check the mechanical capacity of the helical pile. That means we check the tension, compression of the shaft, the bolt bearing. We check also the torque, how much torque that shaft will take. These are, we call them mechanical capacity of the pile. Then we have, of course, the soil capacity. And you will see later on that the soil capacity is the one that almost always controls. Okay, that's the weakest one. Now we have a 278-inch outside diameter shaft over here, and you can see it has 3 bolts. And most of these shaft size, especially for the people who have ICS report, when you go to that ICS report, you have these specs for these helical piles. You will see what is the rating torque. That means what is the maximum torque that you can use to install that shaft into the ground. Okay, so they have rated shaft torque. They have also rated capacity because they have been tested. Okay, and you will see the max torque that pile can be installed to. You will see the torque correlation factor KT for that helical pile shaft, because these are tested, and we find out this KT value. That's why they have them in the ICS report. That's because AC38 requires that you do field testing, tension and compression, to find the torque correlation factor KT for that product. And you will see that not all of them, for instance, the 278-inch outside diameter shaft has a KT value of 9. But when you go to ICS reports and see them in the ICS website, not everybody has a KT value of 9. Sometimes you have a KT value of 9 in compression, but in tension you have a KT value of 8 or even 7. So not always the KT value that you, I'll show you these what is it called, the historical KT value, based on the testing. When you get your ICS report, based on the test results, that's how you obtain the KT value for that product. The helical blade over here, I'll just show you. The helical pile term comes from these helix. Okay, we call it helix, we call it blade, and you can see that these helical plates are pressed in true spiral shape to make sure that when we torque this helical pile in, we make sure that there is minimum soil disturbance. And this twist tip to help pile penetrate hard soil, sometimes we have it only when we have really very, very hard soil. This is a Cantsink helical pile. This is a 278-inch outside diameter shaft. okay, and this is a single helix because it has only one helix. And you can see this structural ribbing over here because in AC58 there are 4 elements. I'll talk about them later on. You're gonna really evaluate 4 structural elements of the helical pile, one of which is the helix capacity. This helix is welded to this shaft. So we go to the lab and we test it. We call it flexural test also because we're gonna bend this helix, and we really testing the strength of that helix. So we find out that if we put this structural ribbing over here, there are like 5 of them, they increased the helix capacity. They increased it from like 30,000 to almost 50,000 allowable. This is allowable. And if you go to our ICCS report 1559, you will see that the allowable helix capacity for the 278-inch outside diameter shaft is like 50,000 allowable. It's like almost 20 or 15,000 pounds more than the others without this structural ribbing. And you can see it's galvanized because sometimes, you see, because of corrosion. And I will talk a lot about corrosion in, I believe, my 3rd lecture, okay? But when you see a galvanized product, that's for corrosion purpose. Now, the benefit of helical pile. One thing I would like you to get tonight is that helical piles, they are so quick to install and they're easy to install. So they are fast and easy to install. Like I said, I installed these helical pile. I told you 278-inch outside diameter shaft is not that heavy. We don't need machinery to pick it up. You have somebody who just pick it up, put it in there, and boom, install it. I will show you. I have a video for like 1.5 minutes. Okay, I brought it because I would like to show you how to install a helical pile, and you will see how fast and easy to install a helical pile. I believe in the last 3 months ago or something like that, I was talking to one of our workers, and they were installing helical pile. They installed like 40 a day. Of course, there is always Murphy's law sometimes if you don't really hit some obstacle or something. If the soil is good, you can install a lot of them per day, okay? And I believe 4 months ago, I was in Florida. We installed 4.5-inch pipe to 93 feet. 93 feet in Panama City, okay? We didn't get torque. We're trying to get 20,000 foot-pound torque. We kept going based on the soil report. We should hit torque. We should have hit torque around maybe 60 or 57 feet. But for some reason, we put like God knows how many, but we didn't get torque. So we decided to grout it to get the capacity. One of the, also for helical piles, if you really need a larger capacity, because like I said, this shaft, they are really rated capacity. They have rated capacities. So for instance, the 4.5-inch pipe has a maximum capacity of like 140 kips ultimate. But if somebody wants to use 4.5-inch outside diameter shaft and the ultimate load like 200 or 250, you can grout it. Okay, ground that shaft and you can increase the axle capacity, and also grouting you can increase also the lateral capacity of the helical pile. The other benefit is it can be customized to meet capacity requirement. Remember, these are manufactured at the plant. If Peter, for instance, ordered this helical pile and for some reason wants some changes, we can change them fast because we manufacture them in the plant and we mobilize them really quick to the site. They can be used in tension and compression. Sometimes these pile, they should resist, for instance, 20 kips allowable compression, 5-6 kips in tension or 10 kips in tension. So they can be used both in tension and compression. Also, helical piles, okay, they can be used as a quality assurance during installation. Because of what? Because of that capacity torque correlation I talked about. I'm going to talk about. Once you know, when you install a pile, you're always measuring the torque. I've never seen somebody installing a pile just like that. They always have a torque indicator or pressure gauges measuring the torque. And the reason why, because of that capacity torque correlation, the final installation torque will tell you what will predict what is the ultimate capacity. Okay, so when you install it and when you get the torque, the final installation torque required, you're sure, okay, that this pile is going to meet the design capacity. So it could be used as quality assurance for installing helical pile. Helical pile, they do not require structure for reaction resistance. The reason why I say that, because there is another type of deep foundation and it's called push pier, okay? I just would like you to know that they are there, these push pier. Push pier, they're just pipes. I've seen them, I've tested them, like 278-inch outside diameter shaft, 203 wall, okay? They don't have helical plates. You just push them against the structure to really, to almost to bedrock, okay? And that's why you don't use push pier in new construction. You have to have some structure. They use structure for reaction resistance. So they use mostly, I've seen them in Texas, for underpinning. Okay, these are called push pier. Whereas helical pile, they can be used for underpinning. I've been using them a lot, and they can be used for new construction. There is no drilling spoil during installation. Also, helical piles, when you install them, you can load them immediately. You don't have to wait for the curing of concrete in the case of concrete piers. Once you're done, you just put the pile cap or the bracket and boom, you can load them immediately. They're adaptable to almost any foundation. There is no vibration during the installation. And like I said, they are very fast and efficient. They are very easy to install and quick. These are just some of the benefits of helical piles. Now, who is considered the inventor of helical piles? If you open any literature about helical piles, you will see the name of Alexander Mitchell. He was born in Dublin, in Ireland, in 1780. So you can see helical piles, they've been around for a long, long time, okay? And his favorite is a famous Maplin Sands Lighthouse. I put it over here. It was built on helical piles, okay? And it was designed by Alexander Mitchell. And the reason why I said they became so popular in the last 30 years or so, that's because of the advancement in installation equipment. Nowadays, we have these hydraulic machines. We can install almost any type, any shaft size. As a matter of fact, about 10 years ago, ExxonMobil from Canada, they sent me a 1-foot diameter shaft with 48-inch helix diameter, and they wanted to test it to see the helix capacity. What is? I don't have the machinery, the big machine that time at CTL Thompson, so I went to the Bureau of Reclamation in Denver, and I tested. They went like, we test like about 10 of them. They went like over 1.2 million pounds. Okay, and I was asking this, I said, what are you guys using this for? They said this is for ExxonMobil, and they're going to install them somewhere in Canada. It's 1 foot diameter shaft with 48-inch helix. Okay, so this is, nowadays, I mean, we have the machinery to install almost any shaft size. And I've been in the world of concrete. I don't know if you know the world of concrete. As a matter of fact, it's going to be in January this year. Usually it's in Las Vegas. I've seen torque motors that we need to install helical pile. It goes to 800,000 foot-pound. It's a huge, it's from Australia. So we have all this equipment for installation. That's why now helical pile, they became so popular. They're all around the world. I've seen them in Brazil, I've seen them in France, Belgium, Netherlands. They're almost everywhere. Now, installation and application. Equipment use, like I said, almost any hydraulic machine can be used for this small diameter helical pile. So you need an installation machine. You need a torque motor, and you need a torque indicator. Nowadays, long time ago, about 20 years ago, I was installing helical piles with pressure gauges. Okay, now pressure gauges, in my opinion, if they are calibrated as a unit with the machine, the hose, everything, then yes, you can use them. Otherwise, they are not accurate. And the reason why I emphasize this point is that when you install a helical pile, you measure the torque. The torque will tell you what the ultimate pile capacity is. So if you don't measure it correctly, that means the ultimate pile capacity that you're going to be talking about is not correct. So make sure that if you're going to be installing helical pile, you use a torque indicator. For instance, I use ProDig. This is just one of the torque indicators out there. ProDig, this is a company in Kansas. I use ProDig. I've been using them for the last 10 years. They're accurate to the foot-pound. And right now, with all these high-tech, I use ProDig. I connect to that torque indicator with my phone, okay? And I can record all the installation from the beginning until the end. And I can just email it to my computer and I can see the installation. I can record it every 0.5 foot, or I can record it every minute. It's really amazing. I mean, with this torque indicator, the one that I use ProDig, it's really very, very accurate. Okay, so pressure gauges, if you want to use them, and I'm pretty sure there are some people out there, they're using them, at least make sure that they are calibrated as a unit with the rig, with the hoses, with everything. Because like when you go ahead and do a load test, you see when you do a loft test, compression test, or tension test, they always tell you make sure that the jack, the pump, and the pressure gauge, they're calibrated as a unit. Okay, so, but I advise using a torque indicator because they are much more accurate. Then you have the drive tool that connects the torque indicator to the pile and the drive pins. Okay, so now I'm going to show you a short video. This video, I told them to do it, and they are installing the pile slowly to just show you how the pile is installed, okay, and how easy and how quick. Well, I told them to install slowly, and they're going to go probably no more than maybe 9 feet. But this installation here, the process is exactly the same if you're going to be installing a pile 90 feet or you're going to installing 5.5-inch pipe. The process is basically the same. Okay, so I'm going to show you this video right now. What happened? This is, I record this video at Cantsink, so you can see this small machine, Bobcat, that the machine operator, only one, and then this is his helper. This is a 5-foot lead section, okay? This is the torque motor. This is the drive tool. He's gonna really put it down on the helical pile there, and then he's gonna put these drive pins. All right. And then he's gonna just screw it into the ground. And that helper there helps with, putting the helical pile, bringing this extension, all this. And also he's gonna help guiding the machine operator to make sure that the pile is installed plumb. You see, he's right now screwing the pile in, and that's a 5-footer, like I said, and that's just a single helical pile with just single helix. And you see there is no spoil, there is nothing. And if they were really doing this for a real project, okay, they're gonna be installing, like I said, maybe 40, even more piles a day if there is no obstacle during the installation. So he's gonna push all that one all the way to the ground. Then he's gonna go and bring a 3-footer extension and install it. Keep going. So this is basically the lead section that went in, the first one with that single helix. The lead section only has a 1 helix. Now he's gonna stop there. He's gonna take this drive pin out. And then he's gonna go and get the extension. In this case, the extension is 3-footer. Okay, now he's gonna go and get the 3-footer extension.
While we're watching it, we do have a question that maybe you can.
Sure.
Where's the torque indicator in this kind of setup?
That's a very good question. Thanks, Peter. For this one, we forget to put the torque indicator. You're absolutely correct. I will show it later on in another picture. You're right. We only have the torque motor, but we don't have the torque indicator. This guy here has a pressure gauge over here. You see these hoses? But that's a very good question. I forget to say that we didn't put the torque indicator there. I will show it in the next. This, like, for just showing it, and I'm going to tell them we have to do another video to show you where the torque indicator should be. Okay. But that's a very good question. Thank you very much. This guy, usually sometimes we do some helical pile around the place. We really don't, this is not like for real project. He has a pressure gauge in front of him right here. He's reading it. But this is just for showing you how the helical pile is installed. But that's a very good question. Thanks you for asking it. We don't have the torque indicator there, but it has to be there for real projects. Now he put that in a 3-footer. He tied the bolts. You see, that's the coupling connection. Now he put the drive pins, and he's gonna keep going. Like I said, this is just for showing you how a helical pile is installed. The process is basically the same. If you have a big shaft, what you need is bigger rig, because small rig, you won't be able to really do it, and bigger torque motor and bigger torque indicator, because these torque indicator also, they have some capacity. You have 10,000, 30,000, 60,000 foot-pound. They just stop to show you. This is, I believe, for solar mount system, if they want to use it. That's the bracket, okay, that they're going to be using on the top of that pile. So you see how easy it is. And believe me, if you're going to go to a real project and you're going to install these helical piles, like I said, sometimes, of course, there is some obstacle we hit when we're installing this pile, but they're really easy. One person can pick up that 5-footer, put it in, put this pile. He has probably that way he puts these bolts really quick, and they keep going. Like I said, one time they were installing them like to 40 feet. They did like 40 a day. So they're very easy to install, quick. You see, it's done. Now I have some photos to show you. This is, whenever you see an existing structure, that means this for remediation, this for underpinning. They are putting this pile to underpin that structure. The same thing over here. One of the things you see how small the equipment is, even tight space over there. You won't be using a driven pile over here. And you can see the labor. There are not that many. Okay. So the other thing, this one over here also, 3 people, they're underpinning this structure. This is a bigger rig, okay, because this is a 4.5-inch pipe outside diameter shaft. Here is, Peter, where is the torque indicator? It's right there. That's a ProDig torque indicator. This is the torque motor, and that's the ProDig, okay? And you see, this is the drive tool and the drive pins over there. This is the torque indicator that we put in there. Okay, we attach it to the torque motor, and then via the drive tool, we attach it to the helical piles. And we're using a bigger rig because this 4.5-inch pipe has a rating torque of like between 20 and 25,000 foot-pound. So if you use a small bobcat, it's so slow. It's so slow. So we have to use a bigger rig and bigger torque motor to install this 4.5-inch pipe. This is, I believe, near Atlanta, installing this helical. That's a 278-inch outside diameter shaft. This one here, this is, I don't know. There has to, because there is no torque indicator over there. They must be using pressure gauges that is calibrated, because there is no torque indicator there. And you can see the water over here. I said they can really install them almost in any condition. This is also underpinning, using a hand machine to install these. I believe this a 278-inch outside diameter shaft also. This in the river, they were, I believe, they're going to have a walking bridge over there, and they were installing 278-inch outside diameter shaft in the river. This is residential, new construction. Okay, this is for new construction for helical piles. And this is remediation. Underpinning, when you have a house, you can see we have the helical piles, and we have this bracket that connects the helical piles to the foundation of the house. This is how an underpinning bracket look like. Okay. Now, I talked about what a helical pile is. You see the main component of a helical pile, the lead section with the helical plates welded to it, and you keep adding section, extension, until you meet the minimum required depth and the minimum required torque. And you can see that helical pile, they are installed in segments. For instance, at Cantsink, we have even a 2-footer and 3-footer like you've seen. That's because sometimes we install them very, very tight space, such as crawl space or basements. We have to go there and install these helical piles. So that's one of the advantages of helical piles too, for being installed in segments. And for underpinning, yes, that's what we do from the side only. That's true for underpinning. Now we're going to be talking design and theory. What I'm going to be talking about in this section is that I'm going to show you how you determine the pile capacity, how you determine the helical pile capacity. Okay. Once you know how you determine the helical pile capacity, you will be able to design a helical pile. And here's how this is design consideration. Here, pile capacity. There are basically three methods, only three methods to determine the pile capacity. These methods are individual bearing plate method, cylindrical shear method, torque correlation, and of course, if you want to really what is the exact capacity of that helical pile, test it. Okay, but this method, the one I'm going to be talking about, the individual bearing plate method, the cylindrical shear method, these two, they are based on traditional soil mechanics. That means we need soil parameter, and they call them also theoretical method. Okay, they're based on traditional soil mechanics to determine the pile capacity. This one here, torque correlation, that's an empirical method, and it's based from, it's really came from load testing, a lot of load testing. Okay, then I'm going to talk about the standard AC358 a little bit more. So, how do you determine the pile capacity using the individual bearing plate method? By the way, when you see the word individual, that means these helical plates, they behave independently from each other. And for that to happen, there has to be some requirement. Like I told you, there is a requirement on the spacing between these helical plates, and I'm going to talk about it. So what does the individual bearing plate method says? This is a triple. You see, we call this multi-helix configuration helical pile, or a triple, since there are three helical plates. The smallest one, always the lower one. So this intention, using the individual bearing plate method is the same for compression or tension. So what does the individual bearing plate method say? It says that the ultimate pile capacity, okay, is equal to the sum of the bearing resistance of each helix. It's that simple. The ultimate pile capacity of the ultimate pile capacity is equal to the sum of the bearing resistance of each helix. That means you calculate the bearing resistance of this one, and this one, and this one, and you sum them up. That's it. Since these helical plates, they behave independently. Okay, and what is the bearing resistance of each helix? The bearing resistance of each helix is basically the area of the helix multiplied by the soil bearing capacity at the level of that helix. You see how easy it is to determine the pile capacity using the individual bearing plate method? Again, is the sum of the bearing resistance of each helix. In equation form, and I'm going to talk about the spacing between these helices. In equation form, the ultimate pile capacity is equal to the area of the helix multiplied by the soil bearing resistance. And in the helical pile industry, we use the Tergazzi general bearing capacity equation. It's basically area of the helix multiplied by CNC plus QNQ plus 0.5 gamma D and gamma. Okay, that's in general. That's the way we use it in the helical pile industry. And you can see this term, how they are defined. AH, that's the helix plate area. C, that's the effective cohesion. Q, that's the effective overburden stress at the level of the helix. And gamma is the effective unit weight. D is the diameter of the helix. And of course, NC, NQ, and N gamma are bearing capacity factors. That they are, you can find them in any almost geotechnical engineering book. Now, I said, this is small diameter helical pile. We're talking about small diameter shafts. So that's zero and small diameter helical piles. Like I said, if you have large diameter helical pile, you're going to have larger helices. So that third term over here, which we call it compression term also, 0.5 gamma D and gamma, you really don't see it when we talk about small diameter helical pile. It doesn't exist. So we have basically CNC and QNQ because this third term is very small. It's negligible. And the other thing also I said, we talked about small diameter shaft. That means the capacity due to friction along the shaft is very small or so. We did some calculation and it's very small, so we neglected. But when we talk about large diameter helical pile, that friction along the shaft plays a big portion of the helical pile resistance. But for small diameter helical pile, right now, we just ignore this friction along the shaft because it's so small. That's why I said for small diameter helical pile, the pile resists load through these helical plates. So basically for small diameter helical pile, you might say that this is really end bearing pile. It's just the load is resist through these helical plates. For large diameter helical piles, large diameter shafts, it could be a combination of friction and bearing. So now you can see that designing a helical pile using the individual bearing plate method requires prior knowledge of the soil property. You have to determine that C, V, NC, and Q, and also the structure design load, including a safety factor. Usually, you have the design working load on that pile. That's what they tell me when I with CTL or Cantsink, these people, they call me, they said, I have the design working load of 20 kips on this pile. And the safety factor is 2. Usually the safety factor that we use with helical pile is 2. There is also the Deep Foundation, I worked on that too. They publish they have a publication about design of helical piles. You can go to DFI and you can buy it. I believe it's $25 or $50. I don't know. But you can see there, it's really a good document. It's about general design of helical piles. They use also a safety factor of 2. The IBC code in section 1810, I forget exactly the number of section there. It talks about helical pile. It has a section there, and they define that the ultimate pile capacity is equal to the minimum, the least of 0.5 PU. 0.5, that's a safety factor of 2. PU, you can use it based on capacitor correlation, individual bearing plate method, load test, something like that. They have like 6 of them. The first 3, I believe, that's soil capacity. The last 3 are mechanical capacity. So it's 0.5 PU, they said. That means a safety factor of 2. Now, these soil parameter, you can get them from soil report, you can get them from lab testing. The reason I show this, because I want you to know that when it comes to design of helical pile, we use SPT block count, the standard penetration test, and a lot. We have so many empirical relationship that they are correlated with the block count N. Even when I have CPT, I really transfer it to N, block count N. There is a relationship there. In our computer program, we really change CPT to block count N. I emphasize this because when you go out there, you're going to be using this SPT block count N a lot, okay? And that's the one that we use mostly to figure out what is the angle, friction angle, what is the cohesion, what is this bearing capacity factor, NC and NQ. I'm going to show you this equation right now that we use in the helical pile industry. Friction angle phi is 0.36 N plus 27. That's what most of the helical pile industry use as a function of the block count. Cohesion, C is equal 125 multiplied by block count N. You can see that sometimes you see this as N divided by 8. It's exactly the same equation, except it's not in pound per square foot, but it's in kips per square foot. And once we have the friction angle, NQ, this is from Meyerhof, but I believe the original one, 1976, it doesn't have that 0.5 there. I believe, I'm not sure, but I have to go back to that paper. But the helical pile industry, they use 0.5 this because it works well with the helical pile design. But at Cantsink, we have our own NQ. This is the one we use, 0.35 e to the power 0.1325 phi, and also NC, we use 14 minus 1.7 log, natural log of N. This is the one that we use in our computer program, and these are based on test results that we have. We use the individual bearing plate method, and we go and do tests, and we really calibrate those and we come up with this empirical equation, NQ and NC. This is an example of soil boring. I'm pretty sure many of you have seen this. This for clay. These are the block count N I'm showing, okay? 14 for 12, 27 for 12. Usually the block count is per foot. This is for clay, and this one here is for sand, okay? For some people who has never seen a boring log, this is how it looks like in general. You can see the block count every 5 feet usually, and it is given per foot. Now, there is a concept, and that's the minimum embedment depth. The minimum embedment depth is a very important concept governing the performance of helical anchor. That means helical piles in tension, okay? Because if the helical plates are installed very shallow, what will happen is that the soil above that helical plate is insufficient to provide the pull-out pressure. And what happens is that the helical pile will fail in the failure mode will be shallow, okay? That equation I gave you for the individual bearing plate method and the equation I'm going to give you for the cylindrical shear method, these are based on deep mode of failure. Deep mode of failure. If the helical plates, they are too shallow, like I said, the soil, the cone of soil above that helical plate, okay, is not sufficient to provide the pull-out pressure of the helical pile. So Meyerhof and Adam in 1968, they came up with minimum embedment depth that has to be larger than 5D. D is the diameter of the uppermost helix, which is the largest helix diameter anyway. So if you have only a single helix, let's say you have 12-inch helix, single one. Based on Meyerhof and Adam, that means it has to be 5 foot deep, okay? Gali and Hanna, they used a minimum embedment depth of 11D. But in 2007, and that should be 2007, when AC58 was issued, we came up with 12D minimum embedment depth. And all these helical pile manufacturers who have their ICS report tested by CTL Thompson for tension, the minimum embedment depth was 12D. For example, if you have a single 12, it has to be 12 feet below the ground surface. If you have, let's say, 8, 10, 12-inch helix configuration helical pile, the 12-inch, the uppermost helix, has to be 12 feet below the ground surface. That's what AC58 requires. And over here, I show you this. This, for instance, a helical pile here, the minimum embedment depth, if this is for this uppermost helix, according to AC58, is 12D, 12 multiplied by the diameter of that helix. For this tieback over here, this is the soil wedge, this diameter here, according to AC358, this helical plate here, the distance from the soil wedge to this helical plate should be 12D according to AC358. Now, I talked about influence cone here because you might have heard about it. They usually use this influence cone to calculate the minimum embedment depth. And my colleague, this is a colleague of mine who did this. Meyerhof and Gali and Hanna, they use this. And I believe the friction, the angle over here, they use phi over 2 or 2/3 of phi. My colleague just used 45 degrees. Basically what he did, he calculated the weight of this column, the weight of this cone of soil, and he equated to the pull-out pressure using the individual bearing plate method, and he came up with the minimum embedment depth. Okay, and the minimum embedment depth he came up with is really very close to what they got, and that's just using 45 degrees. Now, there is also in granular soil, there is what we call this critical depth, okay, which is the limiting depth with granular soil, where further increase in vertical effective stress results in little to no increase in end bearing capacity of the pile. And you will see this almost in any geotechnical engineering book. And in the helical pile industry, we use that critical depth is about 20D. We use usually 20D. D is the diameter of the uppermost helix. That's the critical depth that we use in the helical pile industry. Now, I said there are 3 methods for determining the helical pile capacity. Individual bearing plate method, as I showed you, is just the ultimate pile capacity is equal to the sum of the bearing resistance of each helical plate, okay? And I will show you there is a requirement about the spacing between these helical plates. Now, there is the cylindrical shear method. Cylindrical shear method, like the individual bearing plate method, is based on traditional soil mechanics. Okay, you need this soil parameter to be able to calculate the ultimate pile capacity. This is the same, picture as I showed you for the individual bearing plate method. The ultimate pile capacity using the cylindrical shear method, how do you find it? In the cylindrical shear method, there will be a cylinder of soil that is encased between the lower helix and the uppermost helix. This soil, there is a cylinder of soil, okay? And then the ultimate pile capacity is determined by summing up the bearing, this is intention, the bearing resistance of this uppermost helix plus the shear resistance around this cylinder that is encased between the uppermost helix and the lower helix. That's what the cylindrical shear method says. Now, you can see that you cannot be talking about cylindrical shear method if you have only a single helix pile, okay? To use the cylindrical shear method, you have to have a multi-helix configuration. So again, for the cylindrical shear method, the ultimate pile capacity is equal to the shear resistance around this cylinder that is encased between the upper helix and the lower helix, and plus the sum of the bearing resistance of the uppermost helix. If it's in tension, if it's on compression, you have the same cylinder but you're going to add the bearing resistance of the lower helix. In equation form, this will be Q ultimate is equal, this is the surface area. I missed that question there. But again, for the cylindrical shear method, I saw that question, but I missed it. For the cylindrical shear method,
I can read it.
Go ahead and read it.
Yes, so it's asking the upper helices are larger in diameter, or are there cases with all the helices are the same diameter?
In general, helical pile, the uppermost helix is the largest diameter. It can't be less in diameter than the other. The uppermost helix is the largest diameter. Sometimes they use the same diameter. Let's say 12, 12, 12. But usually the largest helix is the upper one. The largest helix diameter is the uppermost helix. Okay, but you cannot find it the opposite. No. In the helical pile industry, the lower helix is the smallest, and it's like tapered pile, okay? But sometimes you can find they use the same helix size, but the largest helix is always the uppermost one.
All right, thanks.
So in the equation form here, this is the surface area of that cylinder multiplied by the shear strength, there, plus the area of the uppermost helix multiplied by soil bearing capacity, CNC plus Q and Q. This is basically what the cylindrical shear method says. Now, when do we use the individual bearing plate method and the cylindrical shear method? Here's the answer. There were a lot of research done, okay, between the transition from cylindrical to individual bearing plate method, Now, I'm gonna just summarize the results for you based on all these test results. They find out that the spacing between, I'll go back to the spacing, the picture there. Okay, the spacing between these helical plates, almost anybody, almost any helical pile manufacturer I've seen, they have what you call 3D spacing. It's called 3D spacing. What does mean 3D spacing? That means that D, that's the diameter of the lower helix. Let's say this is 8-inch, 10-inch, 12-inch helix configuration. Okay, 8, 10, 12. If this is 8, and that's the bottom one, you multiply it 8-inch multiplied by 3. That's 24 inches. So this 10-inch is 24 inches from the lower one. Now this is 10 and this is 12. What is the spacing of this 12 from the 10? 10 multiplied by 3, 30 inches. So this is 24 and this 30. So that 3D spacing, you will hear a lot about it because I've never seen anybody using less than 3D. All of them, they use 3D. As a matter of fact, the ideal spacing is when the individual bearing plate method is equal to the cylindrical shear method, okay? Because you don't want to have so many, you don't want to space these helical plates far away. You're going to waste a lot of shaft length. And you don't want them also to be so close to each other. You're going to waste a lot of helices. So the ideal is when the cylindrical shear method is equal to the individual bearing plate method. They give you the same results. So based on all these research, AC58 said that the individual bearing plate method will control when the spacing between these helices ranges from 2.6 to 3.4 D. 2.6 to 3.4 D. Now, most of the helical pile industry, including our own Cantsink, we use 3D spacing. It happens to be like 2.6 plus 3.4, like AC58 says. The average is 3. So most of the helical pile industry, they use 3D spacing. And when I say 3D spacing, make sure the D is the lower helix. You start from the lowest. So like I said, 8, 10, 12, this is 24 because 3 multiplied by 8, and this is 30 because 3 multiplied by 10. That's 3D spacing. And if you have that 3D spacing, the individual bearing plate method will control. Therefore, you don't have to check the cylindrical shear method. It won't work. So most of the time, okay, and unless you have a spacing that is very small, such as 1.D or 1D, which I don't know where you're going to find it, but if you ever run to it, make sure you check the cylindrical shear method because it might control, okay? And usually we've seen this in clay. And like I said, you talk about the cylindrical shear method only when you have multi-helix configuration. If you have a single helix, forget about it. It won't work. It's not there. So again, for the individual bearing plate method, it will control when you have a spacing that is between 2.6 and 3.4. Most of the helical pile manufacturer, they use 3D spacing, and the individual bearing plate method will control. You don't have to check the cylindrical shear method. Now, this is a summary of the individual bearing plate method and the cylindrical shear method. Again, these two methods, they use traditional soil mechanics. They use this soil parameter from the soil reports to be able to calculate the pile capacity. Now, you can see both of these. For clay, for instance, use Q CNC. For coarse grain soil such as sand, use Q is equal Q and Q. These are also soil bearing capacities. Now, the problem there, you have to figure out these NQ, these NC, you have to go through all this. So I would like you to take these numbers over here. These are empirical relationship that we came up when we did all these tests in Colorado. Now, these are done in Colorado, okay? Clay and sand is different from other states. But we did this in Colorado, we did hundreds of them. And what we did, we went and we installed these piles. Okay, we have the boring logs, we have the block counts, we know exactly where the block count, how much the block count is at the level of the helix, and we know the torque, and we install them and we tested them. Okay, we test these helical piles and we came up with the result, the ultimate pile capacity, and went back and calculate the bearing capacity of the soil as a function of block count N. Okay, so for clay, the bearing capacity of the soil in ton per square foot, this is not pound, you have to multiply it by 2000, this ton per square foot is equal to 0.71 N. For sand is 0.78 multiplied by N. And for weathered bedrock is 0.85 multiplied by N. So you can see there, you see, this is the soil bearing capacity. If you have the soil, if you have the SPT block count, you can come up with the soil bearing capacity and just multiply it by the helix configuration, the helix area, and you get your ultimate pile capacity. As a matter of fact, that's what I'm still using. I'm going to show you how you can use this. Okay, this is ultimate pile capacity. This is block count N, and this is the helix configuration. You can use this as a preliminary analysis. Let's assume that Peter called me and he said, Moncef, I have this soil clay, soil this for clay, by the way. I have block count of 20. Okay, there I can see, and I have the design working load of 20,000 pounds, safety factor of 2. What is the helix configuration? And again, because I told you, designing a helical pile, you have to come up with a shaft size, helix configuration, minimum embedment depth, and torque, minimum required torque. You see, he said 20,000, what is it? I mean, design working load, 40,000. That's the ultimate based on safety factor of 2. Remember, all these shaft size, like I said, they're rated. For instance, for the 278-inch outside diameter shaft, it's between 60 and 70,000 pound ultimate. So if I use the 278-inch outside diameter shaft, because I know its capacity is 60, more than 60,000, 60 to 70, the ultimate is 40, so I can use the 278. If I use 278, I go like this and go to block count and 20. You see, the single 8, 8, 10, 12, it won't work. So I'm pretty sure I have, what is it, 10, 12, or 8, 10, 12, or 14, it will work. But for this one here, 19-inch will work. Okay, but I'm sure if you put all these combination of the helix configuration there, you will find the most effective helix configuration for that design working load and safety factor. So what you do is just go ahead and take this equation and multiply them by the area of the helices. If you have 810 or 8-inch or 10-inch or 12-inch, you have all these linear, okay, relationship between the ultimate capacity and block count, and you can come up with the helix configuration. It's really easy. I'm still using this today. Somebody sometimes calls me and I go like, let me look at my chart. And I have a chart there and I can see what is the most effective, helix configuration for that design working load and safety factor. And you can do it also for sand and weathered bedrock. Now, torque correlation. So I've shown you there are 3 methods to determine the pile capacity. I've showed you the individual bearing plate method and the cylindrical shear method, and most of the time people, they don't use cylindrical shear because of that 3D spacing. If they ask you, why don't you use cylindrical shear method? That's because the spacing between the helices is 3D, okay? 3D spacing. And the helical and AC58 clearly requires 2.6 or to 3.4. You have 3D spacing, so you don't need to check the cylindrical shear method. Just use the individual bearing plate method. Now, the other two methods, they are based on traditional soil mechanics. This method is an empirical one, and it's my favorite, torque correlation. There is a correlation between final installation torque and the ultimate pile capacity. You see, we go through all these bearing capacity factors and all that stuff to get the ultimate pile capacity. You will see with this torque correlation, if you know what the final installation torque, you can come up with the ultimate pile capacity easily. So what does the torque correlation mean? Here it is. Torque correlation basically says the torque required to install a pile is empirically related to ultimate pile capacity. That means Q ultimate is equal KT multiplied by torque. Torque, that's the final installation torque. We call it final determination torque or final installation torque. KT, that's a torque correlation factor or capacity to torque ratio. Okay, but usually we call it torque correlation factor. That's the one we use. And if you have the final installation torque, let's say you install a pile to a 25 feet deep, okay, you measure the torque at 25 feet, that's the final installation torque, you multiply it by that KT value, you have the ultimate pile capacity of that pile, okay. That's how to use the capacitor correlation. And now this capacitor correlation, we always have a sense from a long time ago that there is a correlation between the final installation torque and the ultimate pile capacity. But this capacitor correlation came to light and became so famous since the publication of the paper by Bob Hoyt and Dr. Clemens from the University of Syracuse at that time. They did 97 tests, all of them in tension, and they used 8 different shaft size from 1.5 inch square shaft all the way to 8.625 inch outside diameter shaft. And they used 24 different test sites, okay? And they used different helix configuration. They test 97 tests. They used the individual bearing plate method, the cylindrical shear method, and the torque capacity correlation method, okay? So when they find out and they test them, they come up with the ultimate pile capacity. And when they did their analysis, they came up with this capacitor correlation, KT value, okay? And they find out that the capacitor correlation has the smallest standard deviation when it comes to prediction of the ultimate pile capacity. That means the capacitor correlation is really more accurate than the other two methods, cylindrical shear method and the individual bearing plate method, okay? So this torque capacity correlation and this KT factor that the helical pile industry they use today, they use them from AC58. These are the same KT value that Bob Hoyt and Clemens came up with in 1989. Now, historically, this KT value, the torque ratio KT, they use depends only on the shaft size. Bob Hoyt and Clemens, and there is also Dr. Perko who wrote that book about helical pile. The KT value they came up with, it depends only on the shaft size. You tell me what the shaft size is, I'll tell you what KT is, okay? But when I did all these tests at CTL Thompson, I find out that KT value indeed depends on the shaft size. That's true. The shaft size contributes a lot to the KT value, but KT value also is affected by the final installation torque, the soil type, the helix configuration. Is it a single helix, multi-helix? What is it? Also, load direction. Is it in tension or compression? Again, I said Bob Hoyt and Clemens, they did 97 tests, all of them in tension. So this KT value they came up with, they're in tension. Okay, that's why when we do some tests in compression, we have KT value a little bit higher. Okay, and as I find out that the KT value for compression piles are higher than the KT value in tension. So here was the KT value used by the helical pile industry. For 1.5 and 1 3/4 soil square shaft, KT is equal 10. It's 10 to the foot to the power minus 1. The unit is 4 to the power minus 1. And these are the same around the world, okay? For the 2 7/8 inch outside diameter shaft, KT is equal 9. For 3-inch round, and I've seen only one single manufacturer have a 3-inch outside diameter shaft, KD is equal 8 and 7, sorry. And for, sorry, it's 8 for 3-inch round shaft. For 3.5-inch round shaft, KT is equal 7. And for 4.5-inch outside diameter shaft, KT is equal 5.5. And if there is any shaft, this is an AC58, if there is any shaft that is in between, okay, you can use that equation AC58, you can come up with that KT value. But if you have a shaft size that is larger than 4.5-inch, it's outside of the scope of AC58. So these are the KT value used in the helical pile industry today. So if you have a 278-inch outside diameter shaft and you're going to go install it, it doesn't matter based on this KT value, if it is multi or single helix or multi-helix configuration, you install it to 5,000 foot-pound. Okay, you install that 278-inch outside diameter shaft to 5,000 foot-pound. The ultimate pile capacity is 5,000 multiplied by 9, which is 45,000 pounds. You see how simple it is. You don't have to worry about bearing capacity factor or these soil parameters. That's how the capacity torque correlation works. And also, torque is indicative of soil shear strength. Okay, there's so many people, they have some papers that they are talking about installation torque and they are really correlated with soil strength. I forgot which one, but if I find it, if anybody wants it, I'll be happy to send it to them. So torque is indicative of the soil shear strength. And as a matter of fact, AC58 clearly said that, for instance, if you have to install helical pile on some job site, but you don't have soil information at all. You don't have soil reports, you have no soil information at all. What do? Use the capacitor correlation, but you increase safety factor 2.5. Okay, this is an AC58. I forget exactly the section, which section, but if you have no soil information whatsoever, you can use the capacitor correlation, use torque, okay, and use a safety factor of 2.5 instead of 2. So you can see how the capacitor correlation, really how easy to use. Okay, you install the pile, you measure the torque, you have that KT value, use it, you can predict what the ultimate pile capacity is. Now, I said that these standard, I call them standard helical capacity torque factors that they use by the industry, they are based only on AC50, on the shaft size. And that's what AC58, this KT value in AC58, they're based only on shaft size. When I did my Ph.D. at Colorado State University, and I said I did tons of them, okay, I find out and I noticed that the KT is not only about the shaft size only. The shaft size, I believe, contributes a lot to the KT value, but I did 799 total tests, okay, and these are on compression and tension. And there are 8 different shaft sizes ranging from 1.5-inch round cone square shaft to 4.5-inch outside diameter shaft. These tests were performed in accordance with ASTM 1143 for compression and 3689 for tension. And the ultimate load capacity was determined based on 10% net deflection. You have to remember, this is really very important, is that KT value I talked about, it's based on 10% net deflection, okay? Based on 10% net deflection test results. I will talk a little bit about this, but later on, because very, very important. And the net deflection is equal to the measured total deflection minus the elastic shortening or lengthening of the pile. Now, after I did all these tests, usually when you do these load tests and you would like to come up with a KT value, you measure the torque, you do the load test, you come up with ultimate pile capacity, you divide it by the torque, and that's your measured KT. I plotted all these test results for these different shaft sizes. By the way, you can see here effective shaft diameter. That's because I plotted all of them square and round together, and AC58 define effective diameter as follows. For round shaft, the effective diameter is just the outside diameter of the shaft. So for round shaft, forget about it. It's exactly the same as the outside diameter of the shaft. For square shaft, the effective diameter is the diagonal distance between 2 opposite corners. Okay, that's what effective diameter means. So as you can see that this data is scattered all over the place, and you can see the R squared, okay, if you know a little bit of statistics, you can see it's very, very low. It's 0.0907. That means that there is no really no correlation based on that R squared. There is no correlation between measure KT and the effective shaft diameter. There has to be something else missing. So what I did, I went ahead and I went ahead and plotted the measured capacity, that ultimate pile capacity, versus D over T. Now, please do not ask me why did I put there D over T. That's because I tried so many other variables such as section modulus, polar moment of inertia of the shaft, nothing. The data was scattered all over the places. So finally, I came up with this effective diameter divided by the final installation torque, and I find out that there is a trend. And look at R squared here is 0.67. This is for all round square compression and tension. From 0.09, I went to 67. That means this 67% of this empirical relationship, okay, is explained. That means 60% of a change of Q measure is explained by the change of D over T. There is other 33%, I don't know. It's not explained, okay? But at least it's better than 0.09. Now I plotted all round shaft, yet you can see R squared is even higher, is 72.9%. For a square shaft, R squared is a little bit less, but it's 55.9%, which is much better than 0.09%. So from this correlation between measured ultimate pile capacity and D over T, the correlation is like of this form: Q is equal lambda alpha D over T to the power beta. So based on statistical analysis, this is what the equation I came up with. Q is equal lambda 282442 multiplied by D over T to the power minus 0.774. I can come up with KT modified. I call it KT here. Is this. Now lambda, what is lambda? Lambda is for round shafts. This is round multi-helix configuration, because I said from the beginning, I'm going to decouple all of this test results. Round multi-helix compression, lambda is 1.182. For round multi-helix tension, lambda 0.996. You see round single helix compression 1.027, and round single helix tension 0.818. You can see the lowest is for single helix in tension for round shaft. For square shaft, square multi-helix compression, you can see the compression is higher, 0.894. Square multi-helix tension 0.798. For square single helix compression 763, and for square single helix tension is 601. You can see that the single helix, if it is square shaft or round shaft, you can see that it has the lowest because of this. You can see the lambda factor over there. Okay, so it's just to show you, I told you that 278-inch outside diameter shaft, that's one of the most common used one out there for small diameter helical pile. So I put this KT value. This is capacitor correlation, KT versus final installation torque. Now, for AC358, KT for 278-inch outside diameter shaft is just 9. It's based on the shaft size only. It's constant. It doesn't matter what installation torque is. Dr. Perko, the KT value for here, the square over here, that's AC58. It's 9. Dr. Perko has 8.5, also as a function of shaft size only. Now, if we really decouple and see this one here, that's round multi-helix compression. You see how high it is? It start, okay? And this one here, the blue one here, the second one, that's round single helix compression. The third one is round multi-helix tension. And this one is round single helix tension. Now, you can see that what I would like you to get from this is this, that this standard KT value that we're using based on AC58 and whatever what the helical pile industry are using based on shaft size only, they underestimate the helical pile at low torque and they overestimate it at high torque. That's what I've seen. So if you have, let's say, 278-inch outside diameter shaft that has a rating torque about 8,000, if you really install it to 4,000 foot-pound, maybe 5, yes, you can get even higher KT value. But when you get near 8,000 foot-pound, that KT value is not 9, is less, okay? And you can see also in compression and tension, there is a difference. Like I said, I find out that in tension, generally, the capacity is about from 10 to maybe 20% less than in compression. And do you know why? The reason why that when we test, imagine you have the same helical pile and you're going to test it both in tension and compression. First of all, when you test it in compression, that lower helix, okay, is sitting on non-disturbed soil. It's non-disturbed. Whenever when you have the tension, if you test it in tension, remember you're pulling on the top soil, which is disturbed. We say that we shape these helices, and the way we install it and all this, we minimize the disturbance of the soil, but we didn't say we completely omit it. There is some disturbance of the soil, and that's why in tension, when you pull on it, that soil is disturbed. Plus, if you look at that equation from when we use the envelope break plate method, when I say Q is equal A multiply AH multiplied by CNC plus QNQ plus 0.5 gamma D and gamma. 0.5 gamma D and gamma, that's the compression term that exists in compression. But in tension, it doesn't exist. Even that small capacity is still there. So that's why we have in tension, we have less than in compression. And based on the test results, I've seen it, it depends. It really varies between 10% to 15 or 20% less than in compression. And that's why when you see here, you see this is around multi-helix compression. See, it's round and it's multi-helix. But the next one is round single helix compression, not round multi-helix tension. Usually multi-helix, they do better than single helix. But you can see here that the round single helix in compression did better, which close, but it better than the round multi-helix tension. And that's because that when you have that compression, in compression, that lower helix is seated on undisturbed soil. Now the same thing for here. This is the 1.5 inch square shaft that I say is very most common, is used mostly in tension. You can see that it's for Howard Perko has it like 11, I believe, as a function of shaft size. It's AC58 is 10, but you can see it as a function of the torque. And 1.5 square shaft, like I said, has about 6,000 foot-pound. That's Cape foot, 6,000 foot-pound rated capacity. You can see at low torque, yes, we have some higher capacity, but at high torque, look at it, a single helix in tension, KT value is about 6 point something. It's not 10 or 11. This is at high torque. So the main point I'm trying to make here is that these traditional historical KT value that they are in AC58, they really underestimate the helical pile capacity at low torque. But at higher torque, they overestimate it. That's the point I'm trying to make over here. Now, this is just capacitor correlation based on KTM, that modified KT that I did is basically the same like I just showed you in that figure. Load test. All right. Now, over here, what we use, this is compression, ASTM 1143. This is tension 3689. Okay. And when it comes to load test, I always say that I advise them to use load cells. You see, that's the load cell and that's the readout. Okay. If you're going to be using pressure gauges, again, make sure it's calibrated as a unit. This jack, the pressure gauge, the pump, all of them together as a unit. And still, I believe the load cell is much more accurate than reading pressure gauges. Okay. This load cell reads to the pound. So this is the test setup for this for tension, this for compression. That's the load cell. Now, how do we come up with the ultimate pile capacity once we did the load test? When you do a load test, what do you record? You record these increment loads and the total pile deflection. Okay, that's what you do usually. And then you go and plot the graph, which is load deflection curve. Now, once we get this load deflection curve, how do we determine the ultimate pile capacity? If you look at the IBC code, I believe there are 3 or more. I know there is Davidson offset limit method. I know there is Branch-Hansen method. I know there is Butler, I believe, or another method. These are at least 3. And if you look at the literature, you probably find 6, 7, 8 different methods to come up with the ultimate pile capacity. But the KT value that is used in the helical pile industry is based on 10% net deflection. What does mean 10% net deflection? That means when you do the load test and you plot that load deflection curve, the ultimate pile capacity is equal to that load that causes, okay, a net deflection equal to 10% of the average helix diameter of the pile. That's exactly what it means. That means when you use 10% net deflection, that's what we use in the helical pile industry, and we call it sometimes the modified Davidson offset limit method. Okay, that means that once you have that load deflection curve, the ultimate capacity of that pile is equal to that load that causes, okay, net deflection equal to 10% of the average helix diameter. Now I said 10% of the average helix diameter. If it is a multi-helix configuration, you take the average helix diameter. If it is a single helix, you just take that single helix. For instance, if you have 8, 10, 12 inch, so you have 8 plus 10 plus 12 divided by 3. So the average helix diameter is 10 inches. 10% of that is 1. Now, in this case, I'm going to show you over here, this is a single 8-inch helix intention. Single 8-inch helix. So from the blue one, that is the total measure deflection. Okay. This one is the red one. That's the net, the net deflection, which is total minus elastic lengthening. So how do I'm going to come up with the ultimate load? I said the ultimate load is equal to that load that causes a net deflection equal to 10% of the helix diameter if it is a single, or the average helix diameter if it's multi-helix configuration. Since this is a single, the net deflection, 10% of what? Of 8-inch is 0.8. So this is 0.8. I go like this to the net deflection. This net deflection, come back here. So this one will give you 48,000 pound. Okay. If you use 48,000 pound, divide by the isolation torque, that's your KT value. If you use any other method, let's say Davidson offset method, this perfect, is going to be conservative. You're going to get less than this. If you use the historical plunge, when we sometimes call plunging. Plunging, when we start pumping that thing and the dial gauges are doing crazy and we cannot increase load. Okay, that's when we say that the pile has plunged. Sometimes somewhere around here. If you use plunging, this one will be probably about 60,000 pound. Now there is a difference between 60,000 and 48,000. So again, these KT value are based on 10% net deflection. If you go and do a load test and use different method other than 10% net deflection, you're going to come up with a different KT value that is different from the standard KT value that we use in the helical pile industry. This is really very important because sometimes people, they do some load tests and they keep calling me and said, how come for a 278-inch outside diameter shaft I get a KT value of 6 or 5? Most of them, sometimes they use different method, like Davidson offset method. Sometimes they don't even go all the way. They don't know what does mean 10% of the average helix diameter. Okay, somebody, for instance, he has a single 12. He stopped the test when total deflection is equal to 0.7. But you have a 12-inch helix. That means you need a 10% net deflection, a net deflection equal to 10% of 12 inch. That means you need a net deflection equal to 1.2. That means the total deflection it depends on the length of that pile, of course, probably about 1.4 or 1.5. You stopped at 0.7. No, you keep going. Okay, so remember that these KT value are based on 10% net deflection. Now, AC358, like I said, it was issued in 2007, and it's accepting criteria for helical pile system and device, and really, it was revised in 2013, 2017, and the latest one, 2020. It really sets the industry standard, tell you the truth. And also higher quality and reliability. Because when you get an ICS report from ICCS, remember, every year they come twice. they visit you twice. They visit the helical pile manufacturer plant for inspection. And that helical pile manufacturer, before he gets his ICS report, they have to have quality documentation. We call it quality control manual, and you have to implement it effectively. Okay, so they come over there and they inspect you from incoming material when you get all these pipes in to the final inspection of the product before you ship it. So they do incoming material inspection, quality control process, and quality control process inspection. They watch you how to swedge these how to punch them, these bolt holes, how to cut them, how to weld the helices to the shaft. They see all that. They inspect it, and you have to have record for that. And then there is traceability, because you have to have all these records. If I say, for instance, I sell a helical pile to Peter, and he goes and install it, and the helix weld broke. He calls me. He said, Moncef, the helical pile broke. And I said, okay, there is a number on that helical pile that I shipped. Give me that tracing number. Give me that number. I go and I trace that number. I see who welded it, who's the welder. I can see that pipe, when did it come, which day, by whom, is it by Excel tube, new core, whatever. I have all that. That's what we call traceability. You have to trace it back to the problem to fix it. Okay, so they have also traceability. They check us, and the final inspection before it's shipped. So you can see there is a lot of work, and all of this to make sure that the manufacturer of the helical pile produce helical pile as good or better than what is described in his ICS report. You see that when you have an ICS report for the product, I usually give this comparison. Imagine, for instance, FDA, okay, for the Federal Drug Administration. There are two medicine A and medicine B. Medicine A is approved by the FDA. Medicine B is not approved. Okay, now medicine B could be as good as A, but when you go and buy something like that, you say, you know what, this is approved. I know it went through all this testing, all this evaluation, but this one, I'm not going to take a chance. I don't know. That's, believe it or not, that's like in helical pile. When you have an ICS report, you know that this product has an ICS report. That means it's code compliant. At least you have a peace of mind, okay? Because they went through all this extensive testing and quality documentation, and also it's expensive. For a single shaft, it takes about $120,000 to get an ICS report for one single shaft. Let's say you have a 278-inch outside diameter shaft and you want to have an ICS report from SCCS, it costs about $120,000 to get it, okay? So it's expensive, but it's worth it. Now, basically, the four structural elements that they are evaluated for helical pile, you have the bracket. You have to really figure out the capacity of that bracket. We call it bracket capacity, and that's connection between the helical pile and the foundation. Then you have the pile shaft capacity. You have to really check it in compression, tension, torque when you twist it. We do the torque rating of that helical pile shaft. It's done in the lab, and it's done in a helix, a coupling, two sections with a coupling to make sure, because we don't do calculation. It's very hard to come up with a capacity rating of that shaft, do calculation. It has to be based on testing. Then you have the helicon plate capacity. That's the helix capacity test that we do in the lab, like I showed you for that structural ribbing that we use for the Cantsink to increase our helix capacity. Then also the soil capacity. We go to the field and we do it in tension, compression, lateral, and we come up with the capacity based on that 10% net deflection. These are basically the four structural elements required to be evaluated according to AC 58. And the soil capacity usually is the one that is the smallest, so is one that controls. We have also a Cantsink capacity calculator. We call it C3. And if you go to our website, Cantsink, it's free. You can go over there, sign in, and you can use it. It's really friendly, very easy to use. All what you have to do is make sure you get the working design load, the safety factor, check which shaft, 278, 3.5 inch or 4.5 inch pipe, which one, and then you enter, like I said, the design working load, the safety factor, and of course the soil property. What is the block count and and what is it, silt, sand, clay, and it will give you the design. It will give you many different helix configuration that will be able to resist that load. Okay, it's really easy. Go and sign in for free, like I said. And you have any question, Peter has my email. You can contact me anytime, email me, and I'll be happy to walk you through that computer program. We call it Cantsink Capacity Calculator C3. Any questions?
Yeah, we did have a question for if Lewis can unmute himself and ask it.
How is settlement calculated? Usually, if you, I will send you also one. I will send you, Peter, that DFI paper that I worked with. We usually use the same settlement that or use the equation from DAS and from other geotechnical engineering book to get the settlement for helical pile. There is one that did, I forgot his name. He's Greek. I always see him in the DFI conference. You see the settlement equation we used, they really, when we did the, when we do the tests, we're not very close, okay? But what he did, he went and he did this test and he calibrated them with the equation. And I need to get, I think I have the paper. When I find it, I'll send it to you, Peter. But one thing for the settlement, okay? Sometimes I tell people, I say, remember, when you design the helical pile, you have that KT, capacitor correlation, am I right? And then that ultimate pile capacity, let's say you have 8, 10, 12 inch, okay? And you're supposed to design it to 40,000 ultimate pile capacity. Design working load is 20,000, okay? Remember, you're gonna say, all right, I'm gonna go to 45. That means KT is equal 9, I'm gonna install it to 5,000, that's 45,000. At 45,000 ultimate, your net deflection is 1 inch. And that's based on test data. Your net deflection is 1 inch. And if it is, let's say, 20 footer, that means the elastic shortening or lengthening is not that much. So your total maybe is 1.05 inch, or that's your settlement that you're going to get. So a design working load, if you're assuming it's linear, it's half of that, but usually it's not. It's not linear. So if it is 1 inch total, usually a design working load should be about 0.4 something or 0.3 sometimes. That's how we get settlement. But the settlement, we use the same equation like the other deep foundation.
Okay, and there's some other questions in the chat, but before we do get there, I wanted to have Lewis ask his.
Yes, my question is just regarding that KT factor again. So you are I guess you're using an expected KT factor before you ever get out in the field. But then how are you back calculating to make sure that you're using the correct one when you're out in the field? Is that revolve around like proof tests or something similar to that?
That's a very good question. Thank you very much for asking it. Quite frankly, based on this project that I did, and I went and did some testing, most of the time, you see this standard KT value, that's the KT value they used on design. That's the KT value they used in design. But when we go there and we test it, usually we test it for settlement and capacity. But the KT value that we use for design is this KT value from the standard from AC58. But sometimes what we do, sometimes I've seen it, what they do, they go and we call it on-site KT value, specific KT value for that project. They go and let's say if they're going to install hundreds of piles, they go, let's say, you know what, let's install like 5 or 6 at different places and come up with a site KT value for that product. Even if 278 inch outside diameter shaft, KT value is 9. We know that. But though some people sometimes they said, you know what, let's go and do some tests before we do production pile to come up with what we call site-specific KT value for that site, just to make sure. And most of the time I've seen them, believe it or not, they're around 9. Sometimes in compression, like I said, and of course it depends on the soil. Even with my KT value, you see how much detail I went through. It really depends on the soil type. and the soil type there in my KT value is not there. I'm working on it right now. I only have the load direction, tension, compression, round, multi, single, but I agree with you. They use that KT value in design before they go there. And sometimes they use load test and they really verify it. Sometimes they don't. But there is one thing for design. You remember I said minimum embedment depth? When you have the soil report, you see the block count. And that block count, when you use the individual bearing plate method, you need that block count to come up with design for the ultimate pile capacity. And also, when you use the capacitor correlation, remember the capacity correlation, you don't need soil information. So the Bob Hoyt and Clemens, when they did the probability, if you use both the individual bearing plate method and the cylindrical shear method, the probability, I think they found like 97%. You have more confidence when you use both of them that the pile will meet the design capacity if you use the torque capacity correlation and the individual bearing plate method. As a matter of fact, AC58, like I said, if you don't have any soil information, use the capacitor correlation with safety factor of 2.5. And again, I saw your question. I mean, usually the KT value, the standard KT value that they're using, that's the one they go with, design with that KT value prior to testing it.
So that, in a way, that's almost just used to confirm the soil conditions that you assumed in design in the first place.
Yes.
Because it's not really related to the soil.
No.
So, okay. Thank you.
Okay, and Randolph asked, how do you know that you have reached the design torque and not just hit a cobble in the soil?
That's a good question, and that will be really good for my next lecture when we have all these situations. First of all, helical pile, they are not good in cobble. Okay, if we hit really cobble, it depends. It's really, I mean, they're not good. We're gonna have problems. Many times I went there and we hit cobbles, and those cobbles, they get stuck in the pitch in the pitch of the helical plates, and we cannot advance anymore. So usually in that situation, you have the soil report. You will see if we have cobble or not. Usually we try to avoid cobble. Okay, we try to avoid it because if we get stuck to it, I mean, sometimes I believe one time we hit cobble. Okay, so what we did, we said, all right, we cannot go through it. Let's just test the pile. We stopped there, and we're supposed to go further to meet the required minimum torque. So we hit it there, and we did some testing, and we came back with good results, so we stopped there. We didn't go more. But cobble will give helical pile problem during installation. That's true.
Okay, thanks. And one more question. What would be some problems that occur with helical piles? I guess you just touched on one, cobbles. And
helical
causes
piles,
of failure.
first of all, yes, helical piles, the problem I've seen, this is based on my experience, Peter. When I hit bedrock, when you hit bedrock, block counts is very high. You cannot go through that bedrock. It's very nice to have your lower helix sitting on bedrock. You're going to get really very high capacity. As a matter of fact, sometimes I get a KT value for the 278-inch outside diameter shaft. I get a KT value of 24. And KT value is 9. And I know why, because there we have bedrock, what we hit, we couldn't go through. We tested it, boom, we get a KT value of 29. Very high capacity because it's sitting on bedrock. The other problem I see with helical pile is that these small diameter helical piles, they don't have lateral capacity. For instance, for the 1.5-inch square shaft, lateral capacity is like 0.5 kip allowable, or maybe even less. For the 4.5-inch pipe, the allowable capacity is like, what is it? I mean, 3 kips max. So for lateral, we have to have some other mechanism to figure out how to resist lateral load. And there are. For instance, right from, if I have, let's say, if Peter wants, let's say 6 kips allowable, even I will go ahead and grout the top 10 or feet, grout it to increase the lateral capacity of the pile. Or I can install them battered to resist the lateral load. So yeah, for instance, in California right now, we're working, trying to get the helical pile in, what is it, category D and F. We're working with the city of Los Angeles right now, the helical pile and tieback committee, trying to get helical pile in there because of the lateral requirement for helical piles. Small diameter helical pile, they have disadvantage on that. The other thing also, large loads, very large loads. Now, there are some helical pile, we can even have commercial building and the helical pile. For large loads, we can use group of pile and the same pier cap, pile cap, I mean. We can use group of pile, okay, to resist large loads. So, and the other thing, based on my experience, and this is basically in Colorado and Texas and Louisiana, sometimes when we have soil, we don't get minimum embedment depth like in Florida. I went 93 feet and I couldn't get torque. Sometimes this type of sand is not really very, I mean, it's not very stiff, very dense layer. It's just start augering. Augering, that means it doesn't want to penetrate anymore. And we go 93 feet and we don't get torque. Usually I will say when you have that type of soil, very low blow counts, and we have to go that very, very, I mean, deep, the only way you can do it is grouting it, and it's going to cost more money. So usually, because a helical pile by itself, if you really install it to 100 feet, look at the elastic shortening and lengthening just by itself. That's a lot, okay? And usually the structural engineer is interested in the total deflection at design working load. Total, not net deflection. So when you have really, you have to go 100 feet and you don't get torque, that's really a problem too. This is just a few I can think of, and if I think of any, I will really email you, Peter. I just saw somebody talking about corrosion, and as a matter of fact, that's the next lecture where I have expensive soil, corrosion, lateral load, and buckling for helical piles. Yeah, sometimes also buckling. For instance, one of the problem with the 1.5 square shaft, if you look at the connection, that coupling connection, the sleeve is like 2 inch. It's very small. When you install it and you see, when you watch it install, it's really very wobbly. And then it's not really plumb when you really install it. There will be some eccentricity, and that will cause problem for buckling. That's why I'm not a fan of using 1.5 square shaft or even 1 3/4 square shaft in compression. It's really very, you will have buckling problem for some large loads. For instance, the 1 3/4, some people, they said it takes 100 kip. I'm not going to use 100 kip on that shaft because KD value is 10. The rating torque is 10,000. That's true when you multiply it. But at high torque, I find out that when I tested, the capacity is used like by 40% or more. So yeah, buckling also is an issue. For corrosion, usually what we do, powder coating, galvanization, we use that. And AC58 has a section about corrosion. And I will tell you right now, I never seen a problem with helical pile when it comes to corrosion. The reason why, if you go to AC58 and look at this equation they give you, okay, even if you take a bare steel and you reduce the thickness by that corrosion, for instance, bare steel, you have to reduce it by 0.036 inches. Take bare steel, and I did it for 278-inch outside diameter shaft. Remember, designing or making a helical pile, the first thing you think of, what? Is designing it for torque, because you have to install it before you put the structure on the top of it. And when you're torquing it, you apply torque, you want to make sure that that shaft resists torque. And if you look at the torsion formula, tau is equal T multiplied by R divided by J. Torque is a function of material specification, that tau is like probably 0.6 Fy, they use sometimes, and J for the same shaft diameter. J increased when you increase the thickness, okay? And the material specification, usually most of these helical pile, they use 50, 60, or 60, 70 KSI. So when you increase the thickness, you increase the torque. So designing a helical pile, first you design it for torque, and that required minimum thickness, it's much more higher than the required thickness for the mechanical capacity of the shaft, because that shaft helical pile, usually they use intentional compression, that's it. So if you really calculate the mechanical capacity of the shaft after you reduce it by 0.036 inches, go ahead and do it. And this is based on AC58. It will take 75 years, I believe, or so to really reduce. But after reducing that, the thickness of the shaft, to get to the soil, the mechanical capacity will be the same as the soil capacity. So you can see the corrosion, usually I don't see it as a problem for helical pile, but we still, because of the codes and because some restriction, we use galvanization and powder coating to really, be code compliant.
All right. You mentioned upcoming presentations, and I was on the website for Cantsink,
Yes.
and I see this. So if someone's interested, I would assume they would just go to the website and sign up through that.
Yes, they will do that, Peter. They will do that.
So if we have only whetted your appetite for helical pile design, you may go to the Cantsink website and sign up for future ones on December 14th and 17th. I would assume you probably covered everything pretty much on the December 10th one. Would that be correct?
Yes, December 10th one is Introduction to Helical Piles, and I probably covered almost more in this lecture, but in December 14th and December 17th, especially December 17th, that's special topics. Like I said, it talks about corrosion, expensive soil, buckling, and lateral capacity of helical piles.
Excellent. And we did record this. Is it okay with you if we put it up on our Central Ohio ASC YouTube channel?
That's fine.
All right.
That's fine, yeah.
Someone asked me about slides. Would you be willing to share the slides that you presented today through email?
Could you please let him send me an email, and because I need to talk to my boss too, because he owns me.
Yes.
Cantsink. Yeah, send me an email and send me his email, and I will talk to him and I'll convince my boss that I can send him the presentation.
I will give you her email. I will do that.
Perfect.
And then
No
your paper in the Deep Foundations Journal, I know I am a member of DFI. If anyone is not a member of DFI and would like a copy of that, just contact me and I can give you a copy through email as well.
Perfect. You have it, Peter. Otherwise, I will send it to you.
I have the that issue of the journal. Yes, I do. Thank you.
Oh, okay. Perfect. Good.
And I think that's it. Thank you very much for this. We have hit the 2-hour mark, so I will be sending out CPD certificates to everyone that was in attendance. And if you don't see anything from me in probably a week, give me at least a week.
Okay.
Hit me up, and I will follow up with you.
Thank you. Thanks everybody for being here today. I really appreciate it. I hope you benefited from this lecture. Like I said, is an introduction. I don't know how much you know about helical pile. But hopefully I will see you soon, maybe in the spring or in some conferences, because I'll be there talking about helical piles again. And thank you very much, Peter. I really appreciate it. Get well soon and talk to you soon. Okay, thank you very much.
All right.
Have a great night.
Bye.
Thank you.